Okay, second video for this week. We're starting a new module. As you remember, we've already done chapter 13. So chapter 13 was on charges. We're skipping chapter 14 and we're moving on to module 15, which is on electric circuits. And I'm bummed because this chapter has a lot of fun things to mess around with, and since we're not meeting in person, it's going to be a little bit harder to enjoy those things. It's not, I don't think, a horribly difficult chapter, so hopefully we'll get through this okay remotely. So remember from module 13, we talked about the different cues and how charges move and if they're attracted to each other or repelled. Well, we're going to build on that a little bit, and we're going to study how charges move when they're restricted to the confines of a conductive material. So how charges move when restricted to a material. Okay, so what am I talking about here? Okay, well, think of all the wires in your house. Or maybe the cord for your iPhone. Okay? These wires and cords are an example of charges moving through in a restricted manner through a material. Okay? When you plug your cord in, okay, the charges can only move in that cord. They can't fly off the cord or whatever. They're restricted to the cord on your phone. Okay? So they can't flow just anywhere. They're confined to the wire or the cord, and they're usually confined by an insulator, so they can't escape the metal, and then they're further confined by an insulator. So by shaping this metal, or by shaping the wire, we can control the electric field, and we can force charges to move where we want them to move to. And remember, those moving charges allow us to use their kinetic energy. And that's how we power things. Okay, so let's start by looking at a battery. Okay, so we're all familiar with what a battery looks like. Okay, it has that little knob on the one top. This is the positive side, this is the negative side of the battery, and they're usually even labeled positive, negative. And hopefully you've taken chemistry, and a very basic understanding of how a battery works is you have two chemicals in here. This chemical wants electrons. It has a deficiency of electrons. This chemical has excess electrons and it's wanting to get rid of them. Okay? So we've got two chemicals separated. One has excess electrons, the other wants electrons. It has a deficiency of electrons. So when we put this battery in something, say a flashlight, the flashlight connects these two ends and it allows the electrons to flow from where they're in excess to where they are deficient. So we have electrons flowing from one end to the other. And again, these electrons then are moving charges, and since they're moving charges, we can take advantage of their kinetic energy. So when we connect the two sides of this battery with a conductor, the electrons can flow. All right, now this whole scenario then forms what we call an electric circuit. Okay, so an electric circuit is just something where the electrons are flowing in a controlled manner. Okay. We want the electrons to travel so we can convert their kinetic energy to work. Okay. Okay, so we take the kinetic energy of these electrons moving, and we can convert that to work. Okay. Now you're probably all familiar with the fact that batteries are rated with voltage. Okay. And that voltage, the more voltage we have, results in the more work that can be done. Okay? And in addition, the number of electrons we have flowing dictates the amount of work that can be done. Okay, so if we had just 2 electrons flowing through here, we would be able to do much less work than if we had 10,000 electrons flowing through here. So the battery's voltage helps dictate how much work can be done, and then also how many electrons are flowing dictates how many work can be done. So this number of electrons flowing is what we commonly call the current. Okay. So electric current, for some reason, I don't know why, is abbreviated with a capital letter I. Okay. And it's the amount of charge that travels past, so moving past a fixed point per every second. My goodness, I'm having issues with my spelling. So the amount of charge moving past a fixed point every second. Okay, so another way to say this is that the current equals the number of charges. Remember, Q stands for charge over a certain amount of time. Okay, and if you remember from module 13, we measure this in coulombs. Of course, we measure time in seconds. Okay, but another name for this coulombs per second is an ampere. All right, and we abbreviate that with a capital A or with the word amp. Okay, so again, electric current is coulombs over electric charge, which is abbreviated with an I, is measured in amperes, and we can abbreviate that with a capital A, or abbreviation amp. Okay, so a way to think about this electric current that maybe will make it a little bit easier is if we think about electric current in terms of a familiar object. So think about a garden hose. Okay, and we all know we can hook the hose up to the house and water can flow through it. So in our example, if we think of the garden hose as being the wire, then the water flowing through we can equate to the current. Okay, so the wire doesn't change. Sometimes we have just a little bit of water flowing through, so that would be a little bit of current, and then that water flowing through when it comes out can do a little bit of work. Or we can turn the water on really fast and hard. The garden hose and the wire doesn't change, but the amount of water flowing through does change, which means our current changes. It's much greater, and the stronger current coming out can do more work. So this analogy might help you understand a little bit what current is. It's just the amount flowing through that wire at any time. Okay, So let's go back to our battery. Okay, so here's our battery again. Here's the little button on the top. This is our positive. This is our negative. Okay, and remember we are gonna hook a conductor up to this. Electrons are gonna flow from the overly negative side to the overly positive side, and that's how we create electricity. Okay, now physicists take this type of a drawing and they have simplified a way to draw electric currents. So let me show you how to do that. They start by drawing two uneven lines. These lines represent the battery. The long line represents the positive node. The shorter line represents the negative node. And then to show the circuit, they draw a rectangle connecting the positive and negative parts of the battery. Okay, so this is our battery. This is our power source. It could also be an outlet on the wall, whatever. This is our power source. Okay. Now we know from chemistry and from our example here that batteries flow from the negative to the positive side. There's an excess of electrons here. Sorry, did I just say the batteries? The electrons flow from the positive to the negative side. Okay, we know that they flow like this. Now, in an electric circuit drawing in physics, it's odd, but we actually draw the electron flow going from the positive to the negative side. And that's called conventional current. Okay, so we know electrons actually flow from negative to positive, but when we're drawing our circuits, we're going to draw them flowing from positive to negative. That positive to negative flow is called conventional current. It's not the way it actually works, but that's how we draw it. And we can blame it all on Ben Franklin, because Ben Franklin understood that electrons were flowing through here, but at that point in time, he thought the electrons did flow from positive to negative. Later on, scientists figured out that wasn't correct, but since electronics drawings had been drawn this way in the past, physicists just kept that convention and we still use it today. Conventional current, okay? So you can blame this backward flow of electrons in the drawings on Ben Franklin. It doesn't change any of our problems, okay? But just realize that they actually flow from negative to positive, but we are going to draw the flow from positive to negative, okay? I have a note here to see figure 15.3 on page 490. So if you're wondering where we're at, I'm on page 490, and this conventional current and this drawing of a electric circuit can be found in figure 15.3 on page 490. Okay, so now we have our battery or our wall outlet, we have our conductor showing a circuit, and we have our current drawn in. So the next thing we're going to talk about is this idea of a resistor. Okay. So all the current flowing doesn't really do us any good unless we have something to hook it up to, like a phone or a toaster or a hairdryer or whatever. All of these things are considered resistors. So anything that we plug in or we use this electric circuit for is a resistor. And these resistors impede the flow of the electrons. So a resistance then is just defined as the ability of a material to impede the flow of the electrons. Okay? So anything that you plug in that uses the electric current is a resistor. Any resistor provides resistance, which is the ability of that material to impede the flow of electrons. So resistance in an electric current is much like friction. And we're very familiar then with friction. Okay, remember, friction impedes the motion of something. Resistance is impeding the flow of the electrons. And just like in friction, kinetic energy is converted to heat or light. That's what a resistance or a resistor does as well. It's using that kinetic energy and converting it to do work. Okay, on your own at home this week, you're going to do experiment 15.1 on page 491. You should have everything you need for this experiment without going outside your home. It just involves a battery and some aluminum foil. So hopefully everybody has a battery that you can use and a piece of aluminum foil. And you'll be writing a lab report for 15.1. It's also important to know that resistance is affected by the type of conductor that we're using and the length and width of the conductor, okay? All right, so finally, let me see, before I go on, resistance is measured in a unit called an ohm. And ohms are abbreviated with the Greek letter omega, okay? So all of what we've learned now brings us to Ohm's law. And Ohm's law is just a relationship between voltage, current, and resistance. Okay, so Ohm's law tells us that voltage equals current times resistance. Okay, again, voltage is measured in volts, current is measured in amps, resistance is measured in ohms. Okay, a common way that you'll often see this Ohm's law represented is with this triangle, split up like so, with the V up here, the I, and the R. If you're a visual person, maybe this will help you. I can just remember this, but if you're more visual, maybe this will help you. If you're trying to solve for volts, it's I times R. If you're trying to solve for current, it's V over R. If you're trying to solve for resistance, it's I over V. It just shows you how to set up your mathematical equation. If you're good with algebra and fine with moving these variables around, this doesn't really gain you anything, but it might help you remember the equation. Okay, so let's look at the units here just a little bit. All right, if volt equals current times resistance, then we know that a volt is equal to an amp times an ohm. We know that an amp would equal a volt divided by an ohm. And we know that an ohm would equal a volt divided by an amp. Okay? So even though these things each have their own unique name in terms of units, we can define them in terms of the units of the other two. Again, just algebra, just pointing that out. So our volts equals our current times our resistance, and this is Ohm's law. Okay, so how do we put all this into one of our circuit drawings then? All right, well, let's start out by drawing our long line and our short line. We're going to draw our circuit around that. To indicate a resistor, the symbol for that in our circuit drawing is a jagged line. Okay. All right. So in our drawing here, this is our, this could be our battery. This could be a wall socket, but it's the source of our voltage. Okay. Here, this jagged line is used to indicate our resistor. All right, and then remember, our current is the electrons moving through. And we're going to draw those in a conventional current going from positive to negative. Our current, remember, is abbreviated with I, and the unit is an amp, and our resistor we measure in ohms. Okay, our voltage, obviously, the unit is volts. Okay, so this is a picture of a complete circuit with our voltage source, the current flowing around, and the current flowing through a resistor. All right, and remember, Ohm's law is V equals I times R. Okay, so let's look at an example. This is 15.1, and it's on page 493. Okay, so example 15.1 says we have a space heater hooked, a space heater with a resistance of 11 ohms. Okay, so we're going to go ahead and just use this drawing. So our resistor in this case is a heater, a space heater, okay? And our our resistance is 11 ohms. Okay, so our resistor is a space heater with a resistance of 11 ohms. When it's plugged into the wall socket, so over here, in this case, we're using a wall socket, not a battery, the heater is exposed to an equivalent of 120 volt potential difference. So our voltage equals 120 volts. Okay. We want to draw a circuit for the heater, determine the current, and draw the direction of the current flow. Okay, so we already have our picture. The current flow, again, we're going to draw in terms of conventional current from positive to negative. That's what these arrows are showing. And we need to determine the current. So what does I equal? Well, we can come back to Ohm's law, V equals I times R. And if we solve for I, we know that I equals V over R. Okay, if we come back to this triangle thing, we're trying to solve for I, so we cover the I up. I equals V over R, voltage over resistance. Okay, we know both of these values. We know the voltage is 120. We know the resistance is 11 ohms. All right, and if we do the math out, 120 divided by 11, we are going to end up with 11 volts over ohms, or I know that volts over ohms is the same as an amp. All right, so my current in this case is 11 amps. All right, so my wall socket is providing 120 volts. My current is 11 amps, and my resistor is 11 ohms. The book says, just to put this in perspective, 11 amps is a lot. If you exposed your body to a circuit with 11 amps in it, you would die. It says most electric chairs, I think it said, were like 9 to 12 amps or something. So this is a lethal amount of current. All right, and then the final, I think the final topic we are going to cover then is electric power. And power is abbreviated with a capital P. So we know from here that 11 amps is a lot of current, but it'd be nice to know how much heat that's actually going to generate with the space heater. And to know that, we need to understand power. So now remember module 8, we studied power, and it was how much energy was used per second, right? So it was like joules per second equals power. Well, while this is true, it doesn't really help us when we're looking at electrical energy. So in this module, when we talk about power, we're going to use the equation P equals current times voltage. And I got ahead of myself here a little bit, so I'm going to go back to this. We talked about how many joules it was per second. We defined power as the change in work over the change in time, okay? And the higher the power, the more energy we had per second. Okay, and then we talked about like a 100-watt light bulb. So 100-watt bulb uses 100 joules per second of energy. Okay, so again, this doesn't help us a lot in terms of electrical energy. So when we're talking about electrical power, we're going to use the equation I times V, or current times voltage, okay? In terms of unit, we're still going to use watt. So a watt is equal to an amp times a volt. So these are just the units. So power, the unit, is still the same. It's a watt, and obviously that must equal an amp times a volt. Start on a new sheet of paper, rewrite this at the top. So power equals IV. The units here are a watt equals an amp times a volt. Okay, and it doesn't take a huge jump then to say, okay, well, I know that V equals IR, so I could substitute IR in for this V, and P would equal I times IR, or I squared R. So both of these are valid equations for power, electric power. And just like some other situations in the book and other modules, you can use either of these equations depending on what information you're given in the problem. If you're given information about resistance, obviously you would use this equation to determine power. If you were given equation or information about voltage, then you would use this equation. If we look at the units down here, a watt then is also equal to the amp squared times an ohm, okay? So just pick the right equation for power based on the information that you're given in the problem. Okay, so let's look at another example. Example 15.2 on page 496. All right. All right, right, in the first part of this example, it says we have a space heater that uses 120 volt wall socket. Okay, so our voltage is 120 volts. All right, and it runs and draws 11 amps of current. So our I is 11 amps. And the question is saying how much power does it use? So we need to solve for power. So we have two equations at our disposal. We are given voltage and current, so this is obviously the equation we want to use, and it's a pretty straightforward plug and chug. Power equals current times voltage. Our current is 11 amps. Our voltage is 120 volts. So if I do that out, our power then is 1,300 watts. I need two significant figures so I can keep it written just like this. All right. To put this in perspective, this would be like 13 100 watt light bulbs. All right, so that space heater has the same amount of power as 13 100 watt light bulbs. All right, so this is a pretty straightforward plug and chug. The second part of the example says we have a motor that draws 1.19 amps of current. So our current is 1.19 amps. Okay, and it has a resistance of 101 ohms. All right, assuming that the assuming that the motor is 100% efficient, what is its power? Well, again, we have two equations for power, so we just look at which is most appropriate based on the information we have. We have current and resistance, so obviously this is going to be the better equation to use. So power equals I squared R. In our case, I is 1.19 amps. We're going to square that times the resistance, which is 101 ohms. And if we do that out, don't forget to hit the square button on your calculator. We end up with 143 watts. Okay. Now this problem did say something like assume that the motor is 100% efficient. So this is never true, but we're going to assume it's true in our problems, and that that the wire or the circuit, let me come back to a drawing, that these electrons are not encountering any resistance except for our specified resistor. Where in real life, these electrons would be encountering some resistance as they flow through the circuit. It just happens, just like we don't have frictionless surfaces. We don't have wires that totally eliminate resistance, but we're going to assume the resistance here is 0, and we only hit resistance in our specified resistor. So that's what that 100% efficient means. It's very similar to where we said ignore friction in many of our problems. Okay. So if you remember going back to this problem in this 143 watts, in Module 8, we use power to determine how far an engine could move something in a given amount of time. So one way to determine that power is by doing calculations like this, assuming that the engine is an electric engine. Okay, that's as far as we're going to get this week. So this coming week, I will post a new homework assignment, but you're basically going to have the study guide for Chapter 12, the test for Chapter 12. That's thunder outside my door. I don't know if you can hear that. You'll be doing on your owns 15.1 to 15.4, experiment 15.1 at home, and a lab report for 15.1. So I'll put this out in a document on Google Classroom, but this is what the coming week looks like. I'm also going to put out a question just about how it's going working remotely, if these Google videos or not Google, if these YouTube videos are working or not, or if you have any suggestions about how to make this a better process. Again, if you have any questions, put them out there on Google Classroom, and I hope you guys have a great week. Wash your hands, don't touch your face, and stay healthy.